A really fascinating stack of material this time.
Yeah, it covers a lot of ground.
It really does. From, basic atomic structure right up to some pretty wild ideas in quantum field theory and even stuff beyond the standard model.
Definitely gets complex towards the end.
Right. So our mission today, basically, is to pull out the most important, the most interesting bits from all this.
Okay.
We want to save everyone some time, get you up to speed on the key ideas about atoms, but, without drowning in every single detail.
Exactly. Think of it like a highlight reel. We start with the atom picture, most people know, but then we quickly ramp up to some really fundamental stuff about how reality works.
Yeah, and you'll see how those basic concepts actually link up to the bigger picture.
They're the foundation, really.
And honestly, there are some cool moments coming up, like how apparently empty space inside an atom isn't really empty at all.
Quantum fluctuations.
And the connections between these tiny, tiny particles and the fundamental forces. It's not just old science stuff, is it? It's chemistry, it's physics, it's driving new tech.
Absolutely fundamental.
Okay, so let's dive in. Let's unpack this, starting right at the beginning. When we talk about an atom, what are we really getting at?
Well, at its heart, the atom is, the basic building block of matter. Your sources lay it out pretty clearly. You've got a central nucleus, super dense, and then this cloud of electrons around it.
Right, the nucleus in the middle.
Yeah, and that electron cloud isn't just random. It's structured into specific energy levels, almost like shells.
Shells, okay. And inside the nucleus, that's where we find protons and neutrons.
Exactly. Protons have that positive charge, and they're what determines the element, the atomic number.
So number of protons tells you if it's hydrogen or helium or whatever.
Precisely. And then you have neutrons, which are neutral, no charge. They add mass and are really important for keeping the nucleus stable.
Okay, so protons give the identity, neutrons help with stability and mass.
You got it. The protons are like the ID card, and maybe the neutrons are, I don't know, the packing material. Keeps things stable.
Huh, okay. But how does that nucleus even stay together? All those positive protons should be pushing each other apart, right? Like charges repel.
That's a great point, and they do repel massively. The electrical repulsion is huge. But there's another force at play, the strong nuclear force.
One of the fundamental forces.
Yes, and it's incredibly strong, way stronger than the electrical repulsion, but only over really, really tiny distances. Basically just within the nucleus.
So it overcomes that push-apart force.
It does. It glues the protons and neutrons together. Without it, only hydrogen could really exist stably. It's fundamental to having, well, the universe as we know it.
Wow. Okay, so we have this tightly bound nucleus. Then the electrons. You said they're in shells, not just orbiting like planets. The sources mentioned energy levels and orbitals.
Yeah, exactly. Forget the simple solar system model. Electrons exist in specific, discrete energy levels or shells. Think of it like an electron can only be on certain steps of a staircase, not in between.
Okay, fixed energy steps.
Right. And within those shells, you have atomic orbitals. You might have heard of s, p, d, and f orbitals.
Vaguely, yeah.
So these aren't neat paths. They're actually mathematical descriptions, probability distributions. They tell you the region of space where you're most likely to find an electron.
So like a fuzzy cloud, not a line.
Exactly like a fuzzy cloud. Think of the electrons zipping around like crazy, and the orbital is just the 3D map showing where it probably is most of the time. And the shape of that cloud, that orbital, is super important for how atoms connect with each other, for chemistry.
So the shape influences bonding. And the sources mention quantum numbers, too. What are those about?
Right. Quantum numbers, they're basically like the full address for every single electron in an atom. There are 4 main ones.
4 numbers for each electron.
Yep. First, the principal quantum number. That tells you the main energy level, kind of how far out the electron generally is.
Okay, distance or energy level.
Then the azimuthal quantum number, L. That defines the shape of the orbital, whether it's an S, P, D, or F-type cloud.
Got it.
Third is the magnetic quantum number, M. That just specifies how that orbital shape is oriented in 3D space.
Orientation. Okay.
And finally, the spin quantum number, S. Electrons have this intrinsic property called spin, kind of like they're spinning, though not literally. It can be up or down.
Spin up or spin down. So 4 numbers define everything about an electron's state.
Its state within the atom, yes. Think of it like a unique ID code. And this is crucial. No 2 electrons in the same atom can have the exact same set of 4 quantum numbers.
The Pauli exclusion principle.
That's the one. It's why electrons fill up shells and orbitals in a specific order, and ultimately it's why the periodic table looks the way it does and why elements behave differently. It's incredibly fundamental.
Wow, okay. So it's a very ordered system, not random at all. Now, things get even weirder when we bring in quantum mechanics properly, right? Like this wave-particle duality thing for electrons.
Uh-huh. It sounds strange, I know, because we don't see it in our big world. But down at the quantum level, particles like electrons act like both particles and waves.
Both? How?
Sometimes an electron acts like a tiny localized particle. Other times it behaves like a spread-out wave, capable of things like interference, just like ripples on water. You need both descriptions to understand it fully.
Okay, that's definitely counterintuitive. And then there's Heisenberg's uncertainty principle. We can't know everything precisely.
Right. Werner Heisenberg figured out there's a fundamental limit. You can't know both an electron's exact position and its exact momentum, which is like its speed and direction at the same time.
Why not? Is it just our measuring tools aren't good enough?
Nope. It's not about the tools. It's built into the fabric of quantum reality. The more precisely you pin down its position, the fuzzier its momentum becomes, and vice versa. It's an inherent trade-off.
So the old picture of neat orbits is definitely out.
Way out. These quantum rules, duality, uncertainty, the exclusion principle, they dictate the whole dynamic nature of the atom.
And these rules have real consequences for how atoms actually link up, right? Bonding.
Absolutely. How atoms form bonds, ionic, covalent, metallic, it all boils down to their electrons, especially the outermost ones.
The valence electrons.
Exactly. They're the ones involved in interacting with other atoms. In ionic bonds, one atom basically gives an electron away, another accepts it. You get charged ions, positive and negative, that stick together.
Like table salt, sodium chloride.
Perfect example. Then covalent bonds are about sharing electrons. Atoms link up by sharing pairs of electrons to get a more stable configuration, like in water, H2O.
Okay, sharing versus transferring. And metallic.
Metallic bonding is a bit different. In metals, the valence electrons aren't tied to specific atoms. They become sort of delocalized, forming a sea of electrons that flows around a lattice of positive metal ions. That's why metals conduct electricity so well.
Ah, that sea of electrons explains conductivity. Makes sense.
And it's all driven by atoms trying to achieve a stable outer electron shell, usually like the noble gases have.
I also read about electrons jumping between energy levels. They absorb or emit photons, light particles.
Yes, that's crucial. An electron can jump up to a higher energy level if it absorbs a photon with exactly the right amount of the difference between the levels.
So it needs a specific energy kick.
Precisely. And when an electron falls back down to a lower, more stable level, it emits a photon with that exact energy difference.
And that energy corresponds to a specific color or wavelength of light.
Exactly. This is quantized, only specific energies work. It's the basis of spectroscopy. By looking at the specific colors of light atoms absorb or emit, we can tell what elements are present and learn about their electron structure, like a fingerprint.
Those are the quantum leaps. Literally. Okay, that covers the sort of standard picture well. But the sources went deeper into quantum field theory, QFT. That sounds like a whole different ballgame.
It really is a shift in perspective, a big one. QFT says that fundamental particles, like electrons, aren't actually tiny little balls. They're more like excitations or ripples in an underlying field that fills all of space.
A field, like a magnetic field.
Sort of analogous, yeah. There's an electron field everywhere. And what we see as an electron particle is just a localized vibration or packet of energy in that field. Same for photons in the electromagnetic field, quarks in the quark field, and so on.
Whoa. So particles aren't the most fundamental thing. Fields are.
In the QFT view, yes. Fields are fundamental. Particles are just manifestations of those fields. It also means empty space isn't empty. It's the ground state, the lowest energy level of all these quantum fields, and it's fizzing with potential activity.
That's mind-bending. Okay, and the Dirac equation came up here.
Right. Paul Dirac developed an equation for the electron that beautifully combined quantum mechanics with Einstein's special relativity.
Relativity for electrons.
Yes, because electrons and atoms can move pretty fast, especially in heavier elements. Dirac's equation was a huge success, and one of its most stunning predictions was antimatter.
It predicted antimatter.
It did. Specifically, the electron's antiparticle, same mass, opposite charge. Finding the positron later was a massive confirmation of Dirac's theory in QFT.
So relativity matters even inside the atom.
Wow.
And QED, quantum electrodynamics. That's the QFT for electrons and light.
Exactly. QED is the quantum field theory of the electromagnetic force. It describes how charged particles like electrons interact by exchanging photons.
Exchanging photons. Like playing catch.
Kind of. But these are virtual photons. They're temporary intermediary particles that mediate the force. They pop into existence for the interaction and then vanish. We don't see them directly, but the maths describing their exchange perfectly predicts how electromagnetism works.
Virtual photons. Okay, so they're like messengers carrying the force.
That's a good way to think about it. And the proof is in the pudding. QED makes incredibly precise predictions. One famous example is the Lamb shift.
The Lamb shift. What's that?
It's a tiny, tiny difference in the energy levels of the hydrogen atom that the simpler quantum mechanics couldn't explain. QED predicts it perfectly. It arises because the electron is constantly interacting with these virtual photons popping in and out of existence in the vacuum around it, the quantum fluctuations of the electromagnetic field.
Do even empty space affects the electron's energy levels?
Measurably so. It's direct evidence for these quantum field effects. Space isn't empty, it's a dynamic environment.
Okay, truly mind-bending. Now, the sources also went inside the nucleus, talking about quantum chromodynamics, QCD. That's the theory for quarks and gluons.
That's right. If QED handles the electromagnetic force, QCD handles the strong nuclear force, the one holding the nucleus together, but at an even deeper level, holding the quarks inside the protons and neutrons together.
So protons and neutrons aren't fundamental, they're made of quarks.
Correct. Protons and neutrons are each made of 3 quarks. Quarks are the fundamental particles here, and they interact via the strong force, which is mediated by particles called gluons.
Gluons, like glue.
Exactly. They're the force carriers for the strong force. Quarks also have a different kind of charge called color charge. Nothing to do with visual color, just a quantum property. Gluons carry color charge too.
Okay, quarks and gluons. And there was something about confinement.
Yes. Confinement is a really weird feature of QCD. Unlike electric charges, you can't isolate a single quark. They only exist bound together inside particles like protons and neutrons.
You can never find a quark on its own. Why not?
The strong force behaves strangely. It actually gets stronger the further apart you try to pull quarks. It's like an unbreakable rubber band. Try to separate them, and the force just increases until it's easier to create new quark-antiquark pairs from the energy than it is to isolate the original quark.
Yeah, so they're permanently confined. Okay. And the nuclear shell model, is that like the electron shells?
It's a similar idea, yeah. Just like electrons fill shells around the nucleus, the protons and neutrons, the nucleons also arrange themselves into energy levels or shells within the nucleus.
Okay, shells inside the nucleus too.
Right. And this model helps explain why certain numbers of protons or neutrons, the magic numbers, lead to particularly stable nuclei. It's when these nuclear shells are completely filled.
Like noble gases for electrons, but for nuclei. Got it. And isospin symmetry, what was that?
Isospin is a concept that helps simplify things when looking at the strong force. Because the strong force treats protons and neutrons almost identically, we can think of them as 2 different states of the same basic particle, the nucleon. It's a mathematical symmetry useful for nuclear physics calculations.
Okay, simplifying concept. Now, going back to the whole atom.
Yeah.
The sources said relativity becomes more important for heavier atoms, affecting orbital shapes.
Yes, exactly. In heavy atoms, you have a lot of protons packed into the nucleus, creating a very strong positive charge. The inner electrons are pulled in very tightly and have to orbit, well, move, at speeds that are a significant fraction of the speed of light.
So they're moving relativistically.
Pretty much. And when things move that fast, Einstein's special relativity kicks in. The electron's mass effectively increases, its energy changes, and this subtly alters the energy levels and even the shape and size of the orbitals, especially the inner ones.
And that leads to things like fine structure in spectra.
Precisely. If you look very closely at the spectral lines emitted by atoms, what looks like a single line might actually be split into several very closely spaced lines. That's the fine structure.
What causes that split?
It's mainly due to spin-orbit coupling. The electron has its own intrinsic spin, like a tiny magnet, and its orbital motion around the nucleus creates another magnetic field. The interaction between the electron's spin magnet and the orbital motion magnet causes a small shift in energy levels. It's a relativistic effect.
Okay, spin interacting with orbital motion, and then there's hyperfine structure, even smaller.
Even smaller, yeah. Typically about 1,000 times smaller splitting than fine structure. Hyperfine structure comes from the interaction between the electron's magnetic moment and the magnetic moment of the nucleus itself.
The nucleus has a magnetic moment too.
It does, arising from the spins and motions of the protons and neutrons inside it. So hyperfine structure gives us superfine details about the nucleus interacting with the electrons.
Incredible detail. And the Zeeman effect, that involves external magnetic fields, right?
Yes. If you put an atom in an external magnetic field, its spectral lines split even further. The external field interacts with all the magnetic moments, electron spin, electron orbit, nuclear spin, and breaks the degeneracy, meaning energy levels that were previously the same energy now split into multiple distinct levels.
And that's useful.
Hugely useful. Astronomers use it to measure magnetic fields on stars. In the lab, it's a precise tool for probing atomic structure and magnetic properties.
Okay, now let's get into the really exotic stuff mentioned. Muonium, positronium, what are these?
Yeah, these are cool. They're like atoms, but with substitute parts. Ammonium isn't really an element. It's an electron orbiting an antimuon. A muon is like a heavier version of an electron, so an antimuon is its positive antiparticle.
So like hydrogen, but with a heavy positive particle instead of a proton.
Exactly. And positronium is even weirder. It's an electron orbiting its own antiparticle, the positron. They're bound together just by electromagnetism.
Why study these?
Because they're purely electromagnetic systems, much simpler than atoms with complex nuclei. They let physicists test QED, the theory of electromagnetism, with incredible precision and study the properties of these fundamental particles like muons and positrons in a clean environment.
Okay, precision tests and antihydrogen. Actual antimatter atoms.
Yep, real antimatter. An antiproton for the nucleus and a positron orbiting it. Creating and trapping antihydrogen is technically very challenging, but incredibly important.
Why? What can it tell us?
The big goal is to test CPT symmetry. That's a fundamental symmetry of nature that says physics laws should be the same if you swap particles with antiparticles, C, reverse spatial coordinates like a mirror image, P, and reverse the direction of time, T.
So antihydrogen should behave exactly like hydrogen, just...
According to CPT, yes. For instance, its energy levels, its spectrum, should be identical to hydrogen's. If experiments find even the tiniest difference, it would be revolutionary physics beyond the standard model.
a huge discovery waiting to happen, potentially.
Yeah.
And Rydberg atoms. Highly excited.
Right. Rydberg atoms are atoms where one electron has been kicked way, way up into a very high energy level, really far from the nucleus.
What's special about that?
They become enormous, physically huge for atoms. They live for a relatively long time before decaying, and they are exquisitely sensitive to external electric and magnetic fields.
So they're like supersized, super-sensitive atoms.
Pretty much. Their exaggerated quantum properties make them fantastic tools for research, especially in quantum computing. Their sensitivity allows them to be easily manipulated as quantum bits or qubits, also used for ultra-precise measurements.
Okay, so this atomic knowledge isn't just theory, it's enabling new quantum technologies.
Absolutely. The level of control we now have over individual atoms is underpinning a whole new technological revolution. Take optical lattices.
What are those?
They're like egg cartons made of laser light. You can use interfering laser beams to create a grid of tiny potential wells, and you can trap individual atoms in each well, holding them incredibly still.
And that's useful for?
Atomic clocks. By probing the energy transitions of atoms held in these lattices, we can make clocks that are unbelievably accurate, the most precise measurement devices humans have ever built. They're essential for GPS, communications, and testing fundamental physics.
Wow. And quantum entanglement. Using atoms.
Yes, entanglement is that spooky quantum connection where particles remain linked no matter how far apart they are. You can entangle the quantum states, like the spin of different atoms.
The spooky action at a distance Einstein didn't like.
That's the one, and
Yeah.
it's real. Entangled atoms are a key resource for building quantum computers, which could solve problems impossible for classical computers and for developing perfectly secure quantum communication systems.
So manipulating atom states is key for quantum information.
Right.
What about Bose-Einstein condensates, BECs?
BECs are amazing. It's a state of matter you get when you cool certain types of atoms, bosons down to incredibly low temperatures, like billionths of a degree above absolute zero.
What happens then?
A huge fraction of the atoms basically lose their individual identities and collapse into the exact same lowest quantum energy state. They start behaving like one single giant quantum wave function you can actually see.
You can see quantum effects on a large scale.
Yes. You get macroscopic quantum phenomena. Studying BECs gives us insights into things like superfluidity, fluids flowing with zero friction, and superconductivity, and helps us understand quantum phase transitions, fundamental changes in quantum systems.
Okay. Finally, the sources really push the boat out, suggesting atomic physics can probe beyond the standard model.
Oh,
Seems like particle accelerators are needed for that.
accelerators are one tool, but high-precision measurements in atomic physics are another complementary approach. It's
Hmm.
about looking for tiny deviations from what the standard model predicts.
Like finding a crack in the theory.
Exactly. Remember those QFT effects like electron self-energy and vacuum polarization that affect energy levels, like in the Lamb shift?
Yeah.
QED predicts those effects with stunning accuracy. If experiments measuring atomic energy levels become even more precise and find a tiny mismatch with the QED calculation, that mismatch could be the signature of a new unknown particle or force interacting with the atom.
Ah, so precision is the key.
Precision is everything here. Same with QCD experiments like deep inelastic scattering probe inside protons, testing QCD predictions.
Yeah.
Relativistic calculations of atomic structure are getting better and better. Again, discrepancies could point to new physics.
What else?
Studying fundamental symmetries. The standard model predicts certain patterns of symmetry violation, like parity P violation or CP violation. Atomic physics experiments are searching for tiny deviations from these predicted patterns, which could signal new physics related to things like the matter-antimatter asymmetry in the universe.
So checking if nature symmetries are exactly as the standard model says.
Right. And studying those exotic atoms, again, muonic hydrogen, where the electron is replaced by a heavier muon, is super sensitive to the proton size. There was actually a puzzle recently where muonic hydrogen seemed to suggest a different proton size than other methods. That kind of tension drives research.
And antihydrogen again for CPT tests.
Exactly. Plus, the amazing control we have over Rydberg atoms and DECs allows for searches for other subtle effects or new interactions. Even trying to create and study super heavy elements pushes our understanding of nuclear forces to the limit, potentially revealing breakdowns in current models.
So it's like attacking the frontiers from two sides, high energy with accelerators and high precision with atomic physics.
That's a great way to put it. They complement each other beautifully in the search for a deeper understanding of the universe.
Wow. Well, we have certainly covered a lot of ground. From protons and neutrons right up to quantum fields and searches for new physics.
It's quite the journey, from the seemingly simple to the incredibly complex.
Yeah, and I think the big takeaway really is that the atom isn't just this static little picture. It's this dynamic quantum dance of forces and fields. It's the foundation for everything, and it's still driving innovation.
Absolutely. It underpins chemistry, material science, biology, everything.
Yeah.
And our understanding keeps evolving.
It really does.
Yeah.
Which makes you wonder, considering how much our picture of the atom has changed, becoming so much deeper and weirder over time, what other areas that we think we understand pretty well might actually have similar hidden depths?
That's a fantastic question to ponder. Where else might seemingly settled knowledge crack open to reveal something completely unexpected if we just look closer or ask the right questions?
Exactly. Food for thought. Well, hopefully this deep dive gave everyone a good, engaging tour through the world of atomic structure.
We hope so. There's obviously so much more to explore.
For sure. This is really just scratching the surface, but hopefully it sparks some curiosity. We definitely encourage everyone to dig deeper into any parts that caught their interest. Thanks so much for joining us on the deep dive.